Our next presenter is Ali Begen. And Ali, if you would, go ahead, turn on your camera and start sharing your screen. That would be great.
Hello, Brett.
And
Let me share my screen. Give me a second.
fantastic. Ali is here to talk about adaptive streaming.
Hello, everyone. My name is Ali. I'm a computer science professor at Özyeğin University, and I'm also a technical consultant for Comcast. And this is a joint work with colleagues of mine from Atlas Stream, Abdul Haq, Bentaleb, and Alex Gladi from Comcast. And a student of mine is also working on this project, Mehmet Akçay. So I have been working on this area for some time, and what I would like to show you some recent results, what we have implemented in the open source dash.js client. And as content-aware encoding becomes more and more popular, we are seeing this across the service providers and streaming providers. We have seen increased amount of failures in terms of playback, and we wanted to investigate this further, and that's what we are going to discuss today. So this is also a preview for a paper that we will be presenting in IBC later this year. Okay, so the problem is quite simple. If you consider what we need to produce in terms of adaptive streaming for ABR video, a lot of things are obviously in motion, but the main thing is that the client is given a manifest file, and then based on the conditions the client is in, it tries to pick the segments that will give him the best quality under those circumstances, right? So this could be the CPU or the memory constraints on the device itself for the playback, or it could be network bandwidth availability or CDN performance, and all kinds of external factors as well. So the main concept here is that this is a client-driven approach, and the client needs to make some observations, and then it needs to make a decision for the future segments. So that's what we call rate adaptation, and rate adaptation algorithms are pretty important in terms of what you are going to get, in terms of video quality, rebuffering performance, and so many other metrics that you can think of. So to date, until very recently, a lot of content has been produced in more or less in a CBR fashion, constant bitrate. And this was mainly done because the client implementations weren't really able to keep up with the varying bitrates. Varying bitrates means if you have a constant segment duration, varying bitrate means it's a different size for each segment, and that somewhat confuses the client in most of the times, and causes problems for the playback. So just looking at an example here, I have a bunch of segments here, as you can see, and the block size is showing the segment size. And if I am encoding these in more or less a CBR fashion, I'm trying to spend an equal number of bits for each segment. This is what I'm going to get. Obviously, as the previous speaker mentioned, none of the encoders are perfect CBR, so there is some tolerance, and it has been more or less around 10% so far. So if it is within 10% bitrate variation, we still consider that as a constant bitrate encoding. However, natural content is not really the same from, in the temporal domain, and the segments have different complexities and different amounts of motion. So when you look at the segment quality, if you keep using the same number of bits per segment, your quality might vary significantly. So for the easier segments, if you have plenty band number of bits, you can really do a very good high quality encoding. For more difficult scenes, maybe bit budget won't be sufficient, so you will end up with really bad quality segments. So in terms of segment sizes, we have a very stable scenario, but in terms of segment quality, things vary quite a bit, right? So, I'm sure you will agree with this, but so many QA studies out there have already shown that if there is really something worse than having to watch a video the bad quality, it is to watch that video with varying quality, like the resolution keeps changing, blocking artifacts, the amount of blocking keeps changing. It is really disturbing to casual viewers. So if we want to encode the content in a more, subtle fashion, which is, content adaptive encoding, or you can call it VBR if you variable bitrate encoding, because that's at the end what we get. What we are going to have is will be something like this. So more difficult segments will require more bits, and the easier segments will need only, few bits. And the overall expectation is we are not going to increase our total bit budget. We are just going to use our budget more, wisely across the segments, so that the overall segment quality will be more or less constant. And then hopefully the overall average segment quality will be higher than the previous case. So, this is a given. Now we are able to use some of this, encoding technologies in streaming, because the clients are getting better, but also the guidelines, for example, from Apple on HLS, they also allow for some bitrate variation. For example, if you look at the latest Apple TV specs, they allow you to go to up to 2x, which is like you can double the bitrate for a short amount of time for on-demand content. But for linear content, it's still up to 25% bitrate variation. It's still not that good, but it's still much better than what we used to have in the past, right? So we don't use more bits, but we use the bits more wisely, and that helps with the quality. Now, the question is, how we are going to stream this content, right? Encoding is easy. I mean, people have been doing a VBR type of encoding for a long time. And, with the more advanced tools, like based on machine learning, AI, whatever you can think of, right? All those tools also help with the encoders in terms of rate control and, quality optimization. But streaming those segments, such content, is still not that easy. So content-aware encoding is just only one part of the whole story. Content-aware streaming is the bigger issue, in my opinion. Now, obviously, people have studied this problem, and then, there have been some proposals out there. And but at the end of the day, we need some running code so that people can actually test this in their environment and see whether it helps or not, right? So, for that purpose, we grabbed the dash.js, one of the most popular open source dash players out there. And, we wanted to implement this. And then on top of that, while we were doing this, we also wanted to improve a couple of things in the player itself. So this is the basic component architecture for dash.js. And as you can see, there are a number of ABR rules, rate-based and dynamic on the right bottom corner. They are the built-in functionalities. And what we are proposing in this work is called SARA, which is size-aware rate adaptation. So that's a component we implemented. But not only that, we also upgraded the throughput measurement and smoothing functions for dash.js, as well as we added a bandwidth prediction component, which I'm going to talk shortly. So dash.js has basic functionality for throughput measurement and smoothing, but doesn't have a prediction component. And with SARA, we also added that functionality, and all this is available as open source. Now, in terms of bandwidth prediction, we have two methods implemented. I'm not going to get into too much academic details, but there are two prediction algorithms that we implemented, RLS and MPC. They function differently. They have different advantages and disadvantages. I'm going to refer to you to the paper if you would like to read more and see what the differences are between those two approaches. So when we look at the default dash.js, the way it works is as follows. Dash.js, after every segment download, you make a request, you get a response. you measure the bandwidth. The way dash.js measures the bandwidth is you know the response size, which is your segment size, and you know the time it took to download it. So you just divide the size by the download time, you get a bandwidth measurement. And this is just one sample. For each segment, you get a different sample. And we don't use these samples right away in our ABR algorithm. What we do is actually we smooth them out because sometimes there are some outliers. Maybe a segment just came from a nearby cache, meaning that your observed throughput or bandwidth was way higher than the other samples. So we need to smooth things out. And for this, the dash.js, by default uses exponential weighted moving average over the last 4 samples or last 4 segments. And then, as I said, there is no prediction. Whatever comes out of that smoothing algorithm will be used in the rate adaptation algorithm, rate-based or dynamic, whichever you pick. For the SARA one, segments size-aware rate adaptation, what we do is we measure the bandwidth the same way, but we do use a different smoothing algorithm, which we think that works better. And that's not exponential weighted moving average, but it's just a simple arithmetic average over the last 3 samples. But we do have this very critical component called bandwidth prediction. And we have 2 different approaches for it. You can pick either one. And this prediction takes the input of the smoothing component and then gives you a predicted bandwidth for the next step. And as a matter of fact, our prediction can be even run in multi-step phase, meaning that we can predict the bandwidth for the next segment. We can also predict the bandwidth for the next and next segment. So we can, predict for the next several segments if our ABR algorithm is able to use that information for making decisions. And then we have our own ABR algorithm, which uses the segment size information, as I mentioned earlier. So this is the flow chart. As you can see, it is not extremely complicated or cumbersome for the client. As a matter of fact, we haven't really have measured any increased CPU usage for this kind of playback. Again, I'll skip the details, but the flow chart is relatively simple. The only thing I want to say is that the left-hand side, the green component, is where the size-aware logic is. We check we know the size of the segments in advance, so we actually take those into account when making a decision. And the right-hand side, the orange boxes, it is an optional feature that adjusts our upshift aggressiveness. So by changing the value for the upshift threshold, we can adjust how quickly or how slowly we will be able to upshift. This is just a parameter that you need to use in the client. So just to give an idea about how the ABR algorithm works. So that this is a very hypothetical, very simple example. So 2-second segments, and we have 4 representations, and these are advertised bit rates: 300, 500, 1000, and 2500 kilobits per second. And somehow our client predicted the next bandwidth, for the next segment will be 0.5 megabit. So, and the critical threshold for this client is 2 seconds. So if the client never wants the buffer to drop below 2 seconds. So here is the table we are given. On the first column, I have the advertised encoding bitrate, these representation bitrates. And based on this, I know the advertised segment size. For example, since these are 2 seconds, we just multiply them by 2. But the actual sizes could be way different than these advertised sizes. In this case, they are way lower than what we would actually expect. Now, the predicted bandwidth is 0.5 megabit, and I have only 1 second of data in my buffer, so I am at the very high risk of rebuffering. I don't really have much, media in my buffer. Based on the predicted bandwidth and the actual size, I know exactly how long it's going to take me to download this next segment, right? And based on that, I can also calculate what the next buffer level will be, what my buffer level will be after I download the next segment. So, so it's a very simple math, and I rounded up the numbers, so it's easier for you to confirm the results. Now, the rate-based algorithm, since it doesn't have a prediction, and not only that, it doesn't know the actual sizes, what it will assume that if its smoothed value is 500, it will just go with the 500 representation. In this case, it will go with this. Yes, it will download a smaller segment, so it will be able to grow its buffer. But our algorithm will check all the possibilities, and then we'll eventually decide on this 1 megabit per second representation. Why? Because I can still sustain a good level of buffer, above the threshold, but I can get a higher quality segment. So I'm able to upshift, whereas the default dash.js client wasn't able to. Now, the next example is a bit different. Now, the buffer is 10 seconds, so the client is already in a good phase. It has enough buffer media in its buffer to start with. The same scenario, it's just the buffer level is different. Now, the rate base will again pick the 500 kilobit per second representation, because that's the only thing it knows. This is what I can get, and this is what I should get. But in this case, looking at the results, we will go even for the highest bitrate representation. Why? Because we know that, yes, it will take more than 2 seconds to download it. I don't have enough bandwidth, but that's still okay, because my buffer will still be okay. My buffer will shrink, but I am still okay. And that justifies the upshift opportunity for this client. Now, there are obviously a number of details, but I'll just show you some examples here in terms of different bandwidth profiles. And for the test content we produced ourselves, it's a mix of 4 videos, 2.5 minutes from each. And it is a mix of different types of content. Like there's a Iron Man portion, there is other slow motion scenes, and so that, and we would like to see the impact of VBR for this kind of algorithm. AVC 2-second segments, 25 frames per second, and these are the average bit rates that we produced for our 4 representations. But as you can imagine, the actual bit rates varied quite a bit. So the bandwidth profiles we used are as follows, and these are from the paper given below. So we took the profiles from that. As you can see, the cascade profile is like a staircase up and down, but over long terms, over the short term, it's pretty stable. The bandwidth doesn't change. The Twitch bandwidth profile is something we collected from a real Twitch server. As you can see, the bandwidth varies quite a bit, but not as bad as the LTE profile, which we also collected from a mobile phone. So we are trying to see how, more dynamic or more stable network conditions will change our results and so on. And this is what our content looks like. So for the first 100 segments or so, it's a pretty, CBR-ish type of behavior. But then, during this portion, as you can see, the encoding bitrate has spiked significantly. So, there's a lot of motion, there's a lot of high action scenes over there. So the bitrate has just spiked. And then over the remaining of the content, it is up and down. So there is some CBR-ish portion, there is some VBR-ish portion, and so on. And the things we are looking into in this study are as follows. So the total downloaded video size, obviously, if you download more, bigger segments, we are going to end up downloading more resources from the server. Total rebuffering duration over the 10-minute content, how many seconds we actually stalled for. And when it comes to rebuffering duration, we separate them into 2: long rebufferings and then short rebufferings. Short rebufferings are the rebufferings which are less than a frame duration, so which is 40 milliseconds in this case. If it is longer than that, it's a long rebuffering. And then the HD performance in terms of the number of 720p or 1080p segments, it's their percentage. and then the specific count for 720p and 1080p. We have 5 different ABR algorithms, the 2 built-in ones, and then 3 flavors from our own algorithm. And here are the results. Now, it's going to look a bit complicated, but I'm going to break it down for you easily. So the total rebuffering duration, as you can see, between the rate-based, dynamic, and then SARA flavors, there's a significant reduction in terms of the total rebuffering duration, and then also the rebuffering count. Short rebufferings are not very visible to the viewers, but they still count. So you can see the results here. If you look at the HD performance, it's very interesting to see that the overall HD performance for rate-based and dynamic are not that bad. But if you dive into the details, you see that they never able to get 1080p content. They are never able to fetch those segments. For Cascade, for Twitch, they download a bit. For LTE, again, they are almost never able to download anything in 1080p, whereas the SARA is able to even half of the segments in 1080p. So when it matters, SARA is able to get the high quality segments, and then hopefully that will give the viewer a better user experience. So if you look at the specific segments where the VBR is way more effective, the segments between 100 and 200, we see that the rate-based and dynamic ABR, which don't take into account the VBR features, they suffer significantly. That's where most of their stallings do happen. Whereas SARA is able to go through that phase without any problem. Actually, it doesn't experience too many rebufferings overall. So that period of time is also pretty smooth for SARA. Observations are, I already mentioned, MPC, RLS, the main differences. I will refer you to the paper. We are now looking into, not just 2-step, but also longer step predictions, so that how we can incorporate it into band, ABR and so on. So this is still an ongoing project, but the initial results are pretty, encouraging. So content adaptive encoding saves bits or improves quality. That's a given. That's not what I'm saying, but that's a given from the encoding people. And by using the segment size information, we are able to improve the performance in terms of HD quality, as well as less stalling significantly. And the bandwidth prediction is not that difficult. We are able to run it in JavaScript with no really extra CPU usage or anything like that. So I think it should be used by any client. And we offer the running code. So if you would like to play with this, go ahead and download the code. So here's a QR code for you. And here are our email addresses in case you have any questions, and some references. That's all, Brett.
Ali, thank you so much.